We want to look at an example of partial differentiation. Actually, we want to look at two examples, and we'll start with this, f of xy, meaning that the function f has two variables, x and y, which is given by equation x squared y plus x times y plus y. And so we want to look at the partial differentiation of x, f of x, or which we can write as df over dx. And so we are going to treat y as a constant throughout, and we'll be dealing with x. So in the same case, in the first case, I'll have 2xy plus y, and then plus 0, which I don't need to write down because the last variable does not contain an x. So I'm only interested with x. And I can also get the second derivative, which you can write it that way, or we can write it in this form. Again, 2 and y are constant, so I'll be left with 2y, and that gives me the final solution for that equation. What about f of y, or the partial derivative of f with respect to y? Let's go back to the original equation. It's x squared y, so it will be x squared, because if I differentiate y, I'll be left with 1. And then plus xy, if I differentiate y, I'll be left with x. And if I differentiate y, I'll be left with 1, because the derivative of y is 1. So what you are doing is you are treating one of them like a constant, but it is not. And then the second derivative that we have, which is d squared f over dy squared, will definitely be equals to 0. Why? Because in C, none of the variables, it's x squared plus x plus 1. There's no y. So x is being treated as a constant. X squared is a constant, so that's 0. X is a constant, that's 0. And y is a constant, that is 0, because we are differentiating with respect to y. So having seen that, we want to look at another simple, maybe a little bit more complex example, just slightly a little bit more involving in the computation, but the idea is the same. And here I'm putting up a problem that will force us to use the knowledge that we have for differential calculus, thinking about the issue of the product rule at the same time. So based on that problem, we want to solve the first part, that is the f of x, which we can write as df over dx. And therefore, I'm going to use the product rule to be able to work with this. And what does the product rule say? So I'll differentiate the first part, sine x, and keep the e constant. So this becomes cos x, e of xy, and then plus, I keep the sign constant, and now I differentiate e raised for xy. How do you differentiate the exponential? You take the power, and the power is xy. We differentiate with respect to x, so you get y e raised to power xy. So that is the first derivative of that f of xy with respect to x, partial derivative, partially, not the full derivation. So I can rewrite this equation. I can rewrite it as e of xy cos x plus y sine x. That is the first derivative of the partial, the first partial derivative with respect to x. Now, I can do the same, that is b, for f of xx, which is d squared f over dx squared. Because I'm more interested, I can use a product rule again, and then I separate. I assume this is one equation, and these are two equations. And that will technically be, if I differentiate this with respect to x, it becomes y, exy, And then I have this part remains the same because I'm using the product rule that we did in differentiation. So I've differentiated the first part because I've said I have two parts, part 1 and part 2. So now my first is I've differentiated e raised power xy with respect to x. So I got y, then plus everything. That is the first part of my solution. And then plus. Now I keep this constant. I differentiate what is inside the bracket. Now, if I differentiate this with respect to x, it will give me that plus this, it will give me that. So that is a solution that I'll get from all those equations that I have there. You note that I can have some like terms or I might not have any to be able to combine them together. And I highly doubt, let me see, that is sine and cosine, and the sine and the cosine. Yeah. So yes, I'll not exactly have like terms per se, but you can put them together if you would like to do so. Now, what about for C, f of y, which is df, the partial, dy. Now you see that I'm only going to differentiate the exponential, so it will be x sine x e raised to power xy, because I've only differentiated this part. And when I differentiate the power of the exponential, I differentiate with respect to y, I get x, which I put down here. Then sine x is x, so I treat it as a constant, and that should give me the solution. So that one was slightly different. What about part D? If I get the second derivative, it will be, everything else will be constant. I'll only be differentiating the exponential, which will give me x squared sine x e raised to power xy. And that's what I'll get. And I could also get the derivative of f of y and then x. That is, I take equation C and now differentiate with respect to y. I'll get xy sine x e raised to power xy. Now, maybe most of you are asking, why is it the case? Remember, when you're differentiating the exponential, you differentiate the power and then you put it on the side. And that's what we normally do. Maybe I'll develop more videos on the normal full differentiation in calculus that we normally have. So I hope you've been able to follow. And again, if you like my videos, please do subscribe. It is nice so that you'll be able to continue to follow what we are doing together. Thank you.